Today we covered the chain rule, and this video will just go through the same worked examples that we did in class today. So recall from last year that we generally differentiated polynomials that had been already expanded, and if we were to differentiate this without any prior knowledge, really what we would do is expand that out and then differentiate the single terms. Now that's possible with maybe power 3, sort of possible for power 4, ridiculous for this one here. So what we need to do is look for a rule that will allow us to do it, and the chain rule is the method for differentiating functions that are written like that. I flashed this up on the screen and then I didn't go any further into explaining what this meant until a bit later on. But what we want to do is we want to recognize what we're actually doing when we're differentiating things with the chain rule. And we use this terminology, or I use this terminology here, of outside and inside function. So let's go ahead and actually do an example, start to talk about inside and outside functions, and note that on the formula sheet, the chain rule is listed as follows: dy dx equals dy du multiplied by du dx. So let's have a look at this one, and then we'll try to do some other stuff with the function notation and stuff that's written above there. So when we differentiate, I want to use Leibniz's notation. So I'm actually just going to say let y equal 2x plus 3 to the 3. Right, now that this is the case, what I'm going to do is look at this thing here. This is what I'm going to call the inner function, and I'm going to say that u is the inner function. Okay, so u is equal to whatever the inner function is. Now the outer function is whatever this thing is to the power of 3. I'm going to say it's y equals, and it's 2x plus 3 to the power of 3. Now that's u to the power of 3, so I'm just going to write it as u to the power of 3. Right, because I'm going to use the chain rule, which is listed above there, what I'm going to do is find out what du dx is, which in this case here is the derivative of that, which is 2, and dy du is equal to 3u squared. Now we'll note here that that is dy du, which is what I've just found there. That's the derivative of the outer function multiplied by this thing here, du dx. Du dx is this thing here, what we call the inner function. Okay, so to find out the derivative of this here, what I'm going to do is multiply the outer function by the inner function. So let's do that. Dy dx is equal to the outer function, 3. Note that this is a u. I'm not going to write u in. I'm going to actually put my definition of u in here. 2x plus 3 squared. And then I'm going to multiply that du dx by this thing here, by du dx, or in this case what I found it out to be, which is 2. Now, I know that this is a bit silly, but I'm just going to put that in some brackets just to emphasize a point later on. Okay, so that's multiplied by 2. Now I'm going to multiply this out, so dy dx is equal to 3 multiplied by 2, which is 6, or 2x plus 3, excuse the look of that 2 there, to the power of 2. And there's my derivative. So again, even with explaining this for the first time, this is a really quick derivative. Okay, and I can bang this out with a bit of experience in, seconds, 20, 30 seconds quite easily. Okay, you'll need to be able to do this using function notation as well. So what I'm going to do is just note down this thing here. I'm going to write down the inner function. So what I'm going to call my inner function is g of x. That's my inner function. And I'm going to call that 2x plus 3. So g of x is this inner function. Also note my outer function is this thing here, x all squared. Right, now let's just check whether a composition of these two will make up this function here. So what I'm going to do is f of g of x. All right, and that basically says that anytime in f of x I see an x, I'm going to replace it with whatever my definition of g of x is, which is this. So I'm going to see the x, replace it with 2x plus 3, and cube it. And what we get, this composition, is exactly the same as that. Okay, So when a function is composed like this of another function, what I do is I find the derivative of the outer function and multiply that by the derivative of the inner function. So let's get the derivative of the outer function. F dash x is equal to 2, and the derivative of the inner function, which is 2. Oh, that was 2x over there. Made a little mistake there. I've written that as the outer function as x squared, as x to the 3, which means that this should be 3x squared as the derivative. My apologies. Okay, so now what we're going to do is to find out the derivative here, we're going to we'll list this as a composition, f composition g, dash x, the derivative of the composition is equal to, what I do is I get the derivative of the outer function, which is this thing here, 3. Now notice this x here, okay, I'm going to replace it with whatever g of x is, okay, g of x is this, 2x plus 3, all squared multiplied by the derivative of the inner function, which is 2, multiplied by 2. So 3 times 2 is 6, 2x plus 3 squared. Right, so that's how I do the derivative with function notation. More generally, fg dash x is going to be the derivative of the outer function, which is f dash, using the inner function, which in this case is g, multiplied by the derivative of the outer function g dash x. And you'll notice that this formula here is this one here. All right, that's this one here. Okay, and so that's how we do it using function notation. I find Leibniz's notation ridiculously easy to work with, and function notation, I do have to think about that a little bit. So I tend not to like using it, but I need to know how to use it, and I'll explain why in a sec. Let's go on to another example here, and you really start to see the benefits of using the chain rule with a problem like this. So I'm going to go y equals, or let's say let y equal, bracket 4x to the 4 take x to the neg 3. Right, so let's go through the same process that we did last time. U is the inner function, 4x to the 4 take x, and y is the inner function to the negative 3. Okay, it's whatever this is, the inner function, to this, and that will be the outer function. Now let's derive du dx, the inner function, which is 16x to the 3, take 1, and let's derive the outer function, which is dy du equals negative 3u to the neg 4. Okay, so you remember that the chain rule is dy dx equals the outer function dy du multiplied by the inner function du dx. Okay, so if you can actually remember that without having to look up the formula sheet, that's really good. Okay, and so remember to just say to yourself the derivative of the outer function multiplied by the derivative of the inner function. Okay, so let's do the derivative. Dy dx equals the derivative of the outer function, negative 3. Now I'm not going to write u down because u is this, 4x to the 4 take x to the neg 4 multiplied by, again, very important that we put this in brackets, and the reason is that this is a 2-term, it's multiplied by all of it, so it's going to be 16x cubed take 1. So it's very important that we get those brackets in there. All right, so now what I'm going to do is note that I've got a negative power here, and if I had to sub values for x in and then evaluate a negative power, it's very difficult to do that. So what I'm going to do is write this with a positive power. So this equals negative 3 multiplied by this thing here. So I'm going to write 16x cubed take 1. So it's negative 3 lots of that. And I'm going to grab this portion of the equation, or this, if you consider only this side the expression, I'm going to put that into the denominator, which is 4x to the 4 take x, and I'm going to write that with a positive power, remembering that a shift from the numerator of a negative power into the denominator makes the power positive. Okay, if you need to read more about that, just Google or YouTube neg index rule. Okay, and you'll find plenty of people who probably put out some good videos of that. All right, so on to the next question. So this came off the VCAR 2012 exam, and I think it was 49% got this right. So roughly 1 in 2 students in the state could do this, or couldn't do that, depending on your glass half full or glass half empty. All right, so let's have a look at why this problem was difficult. Given that g is a differentiable function, so it can be derived, and k is a real number, the derivative of a composition, this is a composite function, is one of these things. So because we're deriving a composite function, we need to understand that actually this is like a composite function here. So that's the chain rule. So we need to use the chain rule on this problem. The issue is if you fall in love with Leibniz notation, it's very difficult to do that when we've got functions written here. And in particular, I've got a function g of x and I don't even know what it is. So it's very hard to do that. So what I'm going to do is I'm going to list the outer function. My outer function is g of x. And what is g of x? Well, I don't know. So it's just going to be g of x. My inner function, I'm going to call that f of x, and I do know what my inner function is. It's e to the kx. Okay, so remember that if we're deriving a composite function, it's the derivative of the outer multiplied by the derivative of the inner. So I'm going to get the derivative of the outer, g dash x is g dash x, whatever the derivative is. And f dash x is the derivative rather of this here, and I don't know how to do that yet. All right, so what I'm going to note here is that my calculator, because this is the calculator section, will actually do that for me. And you can see here, this is me from earlier in the day working the problem. I've just diffed e to the kx, because it's a multiple choice question. Remember, I'm allowed my calculator in this section. So I've diffed e to the kx. That's told me that the answer is k e to the kx. All right, let's get rid of that. All right, so we're going to note that the derivative is going to be the derivative of the outer, okay, so g dash. Now this x here is actually this part here. This is the inner function. So I'm going to stick the inner function in, which is e to the kx, multiplied by the derivative of the outer function, which is k e to the kx. Can't see that anywhere, but there's a simple one there. The answer is going to be A, and because what they've done is they've moved that k, g dash, e to the kx, and got rid of this multiply sign and put e to the kx in there. So our answer is A. So you can see there the importance of understanding how function notation works with that problem. Okay, finding the gradient of the tangent to the curve, and this is the curve, okay, and we want to do it at the point where x is equal to 1. So how do we find the gradient of the tangent? Well, remember that if we find the gradient function or the derivative of this, that will be the gradient function, and then we're just going to simply bang x equals 1 into the derivative to work out what the gradient of the tangent is at that point. So I need to derive this. And really, it looks a lot different to the problems I've been doing. It doesn't look like a composite function. But I can actually do a really quick move to make this look like a composite function. 2x squared take 1. And I'm going to use the negative index law to make it. Okay, so here's my composite function with the inner being this and the outer being 8u to the negative 1. So let's go through the process and write our u, our inner function. 2x squared take 1. Our outer function is 8u to the neg 1. All right, let's work out du dx equals 4x, and our outer function is dy du equals negative 8u to the neg 2. Right, so let's grab our derivative. dy dx, remember, is the derivative of the outer, which is this one here, -8. I'm not going to put down u. I'm going to replace it with this thing here, to the -2, multiplied by, again, in brackets. Very important that we just get in the habit of just stick it in brackets, even if it's a single term. Doesn't matter. Right, so there it is. Now we do have to sub in a value for 1. We've got a negative index here, so we want to make the negative index positive. So that equals negative 8 times 4x is 32x over grabbing this portion which has a negative index and dropping it into the denominator. 2x squared take 1 squared. So that's dy dx. All right, now what I'm going to do is sub in a value. So dy dx with x equals 1 is negative 32 times 1 over, what do we got here? 2 multiplied by 1 take 1 all squared. And that is negative 32 over 2 times 1 is 2, take 1 is 1, 1 squared is 1, negative 32 over 1, which is obviously negative 32. So the gradient at x equals 1 is negative 32 for this function. All right, looking pretty nasty this one here, but again, it's probably got a bit more bravado than you know, it's not that hard a problem. All right, so let's get stuck into it. I'm going to rewrite this a little bit to set it up for the chain rule. Y equals x squared take, because I want to derive this term here, this is going to be my u. I need to get all the x's into the numerator. So I'm going to write this as 5x to the -1, okay, using the negative index rule. And I'm also going to write that as a power. Remember, third rooting something is the same as raising it to the 1/3. Right, so now it's all set. This is now looking very much like a composite function. So u equals x squared take 5x to the -1. Y equals u to the 1/3. Du dx equals 2x plus 5x to the -2. And dy du equals 1/3 u to the, so I need to take this down by 1, so I'm going to subtract 1 off that. So subtracting 1 from that is the same as subtracting 3 on 3 from that. So 1/3 take away 3 on 3 is equal to -2/3. So the power is going to be -2/3. Right, let's use the chain rule. Dy dx equals the derivative of the outer, 1/3, u, which is this, multiplied by the inner, remembering to use our brackets, 2x plus 5x to the -2. All right, let's tidy this up and get rid of all these negative powers. So all right, so now what I'm going to do is grab this negative power, drop it into the denominator. So I'm left with 2x plus 5 over x squared over 3, running out of room, x squared take 5x to the +2/3. Once that goes into the denominator, it becomes positive. All right, so we had a bit of a discussion about this in class, so that's a pretty good derivative there. And what I did at this point was busted out the calculator and worked out the derivative of that, and noted that the calculator makes an extra simplify move. Okay, so this is their derivative of that original function. Right, so mine looks sort of right, but it looks different, and I wonder why. Now, what the calculator doesn't like doing is this idea of a fraction over a fraction. So what it's going to do with this top line here, the numerator, is it's going to find a common denominator. All right, now our common denominator is going to be x squared. So I'm going to make this with a denominator of x squared, or I'm going to make an equivalent fraction. So dy dx equals, so I'm going to multiply this numerator by x squared and the denominator by x squared. That's going to give me 2x to the 3 plus 5 all over the big denominator of x squared over 3 x squared take 5 over x to the 2/3. All right, and what we're doing is, I'm just going to use a bit more room here, so go away calculator, is I'm going to write this as dy dx equals 2x to the 3 plus 5 over x to the 2 divided by 3 x squared take 5 on x to the 2/3. Now dividing by a fraction is the same as multiplying by its reciprocal, which means this is the same as 2x to the 3 plus 5 over x squared times 1 over 3 x squared take 5 over x to the 2/3. Right, because we multiply that out, we're going to get 2x to the 3 plus 5 times 1 is just that, over 3x squared take 5 on x to the 2/3. And I believe that's what the calculator got. Here it comes. Yep. Okay, so that's how the calculator did that, is it just grabbed that common denominator for the numerator and did that. Did I have to sub anything in? No. All right, so here's Mr. Tench's advice. You could watch me do many more examples, but it's your turn. The only way to get better is to do many, many questions. So there's your questions from 3E, it's those ones. What I went on to do then is differentiating rational powers, which is actually what we've just been doing, okay? So this should be the formalization of that. Because it was nearing the end of the lesson, I was not inclined to do this. But what I did was, instead of using first principles, I just did it by rule, okay? And the rule is exactly the same as every other derivative that you've done. So f dash x, the derivative, half multiplied by 3 is 3 on 2, x to the negative a half. A half take away 2 on 2 is negative a half. Right, and then I just gave that a bit of a kind of nip tuck, expressed that as a negative index. Look, I'm jumping a step there. 2x to the half. So I've grabbed that and stuck it in the denominator. And then I'm noting that anything raised to the half is the same as square rooting, which also explains why this seems to be there. Okay, so differentiate where x must be greater than 0, because over here you can only square root a positive number or 0, but if I square root 0, the denominator ends up with 0 and I get divide by 0 error. Okay, so that's why this sort of weird statement actually comes into the play. So there's a lot more space on this page to allow for the first principles, but in the end I pulled the pin on that, just not necessary. Right, so what we're going to do is differentiate this. So again, we're going to say let y equal the expression. Okay, and then we're going to find the derivative dy dx equals, right, so I'm going to do 3 lots of negative 1/7 is 3 on 7x. I need to remove 1 from this or remove 7 on 7 from it, which is going to be negative 8 on 7. Take away 3/5 of 2 is 6/5 x, and I need to remove 1 or 5/5 from this, which is negative 2/5. Okay, so there's our derivative. Let's clean up these negative powers. Negative 3 over 7 x to the 8 on 7. Take away 6 over 5 x to the 2/5. So there's that problem there, and then I could, in theory, sub in a value for x, although how am I ever going to work out the power 8 and then the 7th root of that, I don't know, but I could, I suppose, if the number's easy enough. Right, differentiate the following with respect to x, noting that this is what I'm doing. And again, this is just a basic chain rule problem. So let y equal 2x cubed, take x plus 1 to the 1/3. Right, so now I'm going to set it up, or it's all set for the chain rule. So u is 2x cubed, take x plus 1 y is equal to u to the 1/3. Let's get our derivatives. Du dx equals 6x squared take 1, and dy dx is equal to 1/3 u. I need to remove or get that down by 1, so that's 3 on 3 removed from 1 on 3, negative 2 on 3. Right, let's do our derivative. Is the outer function 1/3 u, which is this, 2x 3x plus 1 to the negative 2/3, multiplied by the inner, which is 6x squared take 1, again noting the use of brackets, equals. All right, I'm going to grab the negative power, drop it into the denominator, multiply the numerator, or 1, by this number here. So I'm left with 6x squared take 1, and keep the brackets or remove them at this point if you want. 3, 2x cubed take x plus 1 to the 2/3 expressed as a positive. Okay, so that was the last example I did, and the bell got us. I really rushed through that last one. I wasn't too worried about that because it is pretty much similar, if not the same, as a question like this one here, all right, with the fractional powers. So that's your homework, is 9E and 9F, I presume, 9F. And there's a little teaser for the next lesson, the product rule. Cool.